All the tests that we have considered so far are so-called parametric statistics. So we are actually using distribution parameters and sample parameters in order to do the testing. But there's also a family of non-parametric tests, and they are used in different cases. One of them is so-called Spearman rank correlation. So this is a coefficient which is non-parametric measure of statistical dependence between two variables. And it assesses how well the relationship between two variables can be described using a monotonic function. If there are no repeated data values, then a perfect Spearman correlation of +1 or -1 occurs when each of the variables is a perfect monotone function of the other. And Spearman's coefficient, like any other correlation calculation, is appropriate for both continuous and discrete variables, including ordinal variables. But what's the difference between Spearman rank correlation and the usual Pearson correlation that we know? Well, in Pearson correlation, we always look for linear dependence. So when you have data points, you would be fitting a straight line. That also means that if you have data points which seem to have maybe quadratically looking dependence, in Pearson correlation you would be still fitting a straight line, and of course it may not be that appropriate. But if you consider that you're fine measuring the level of correlation between the two variables using nonlinear function but monotonic one, so there is still the relationship that when one value increases, the other one increases as well, be it quadratically, with a square root ratio, and so on. So this is where we can change the values of our observations into ranks, so which place they take in their own sample, and then we calculate correlation between those two ranks. So this is what is called Spearman rank correlation. So basically for the two variables x and y, we convert them into ranks, and then we calculate classic looking correlation coefficient, but not between variable values, but between the ranks. If the observations are non-repeating, then everything is fine. If they are repeating, so for instance, if I have 20, 15, 15, and maybe 17, so if I were to rank them, let's say from smallest to biggest, these ones would be 1, 2, 3, and 4. But since these two are the same, so they both would actually get the average, so rank 1.5. That's how we treat repeating observations in this case. And that big correlation formula actually simplifies into such one. So now if D represents the differences between the ranks, so we can calculate that rank correlation coefficient as 1 minus this formula. So we sum up the rank differences squared, and then we divide by population size times squared population size minus 1. Once that correlation coefficient is known, we can verify the level of correlation using Ttest. So null hypothesis in correlation testing always means no correlation. So we assume that rho is 0. Of course, correlation can be strongly positive, strongly negative. That's why it's a two-sided test. And the t-statistic is calculated by simply rescaling our rho correlation coefficient using this formula. And then we fail to reject null hypothesis in case t-statistic is close enough to 0, and we do reject null in case it's sufficiently far away from 0, so beyond the critical values on the left and right hand side. And the number of degrees of freedom here differs from what we had in other t-tests. Now we have 2 samples, but n pairs to be compared, so that's why degrees of freedom is n-2 and not n-1, which would be normally in one population testing t-test.